Okay, we're going to do some more review on chemical kinetics. We're going to talk about activation energy and the Arrhenius equation. Again, when I'm doing problems, I'm borrowing those problems from the text Chemistry by Riddell and Navidi from West Publishing in 1990, a book that I had on my shelf. Okay? So in our first reaction, we've got nitrogen dioxide reacting with oxygen in the gas phase to make nitrogen monoxide and O3, which is ozone, right? All in the gas phase. And we're told what the heat of reaction is. It is an endothermic reaction, that it is absorbing heat energy. And then we're also given the activation energy. And so they want us to sketch a reaction energy diagram given that information, right? You need to this helps us see if you understand what that information is. So in our reaction energy diagram, right, we've got relative energy on the y-axis, and we've got time, sometimes called the reaction ordinate, on the x-axis, right? A measure of the progress of the reaction over time. And usually these are very short time scales, sometimes in the range of nanoseconds, right? So these are very short time scales. Okay, so if we're given this information, right? And so we will use R for our reactants and P for our products, just to make it easier to draw here. So this is an endothermic reaction. So if our reactants are here, then our products end up at higher energy, right? So this is an endothermic reaction, right? And so this is delta H for the reaction forward, and that is our plus 199 kilojoules, okay? Now, the activation energy for the forward reaction, as written, is 209 kilojoules. So if that's plus 199, then our peak here, right, this is going to represent our activation energy, right? So our activation energy is plus 209 kilojoules. And so if we're tracing this, we got to go from here up to the 209 and then back down to the plus 199. Okay? And remember, right, every point along that curve corresponds to an arrangement of atoms. The arrangement of atoms that corresponds to that peak we call the transition state, sometimes shown like that. So the transition state is an arrangement of atoms that corresponds in energy to the peak of that activation energy barrier between the two, right? And so now that expresses the forward reaction. But we can consider, if we extend this line, right, we can consider the reverse reaction, right? So the delta H for the reaction in reverse would be minus 199 kilojoules, right? From here back down to there, right? But now we have to consider the activation energy barrier for the reverse reaction. So we're going from plus 199 on our scale to plus 207 on our scale. That's just a difference of plus 8 kilojoules. So our activation energy for our reverse reaction is just plus kilojoules. And so we can express the reverse reaction as well once we have a good look at our reaction energy diagram. Let's remind ourselves about our forms of the Arrhenius equation. The basic form of the Arrhenius equation is that the rate constant K is equal to A, the Arrhenius constant, that is, and it's a constant that's related to the identity of the chemicals that are reacting and the kind of reaction that is occurring. So it's different for every kind of reaction, right? Raised to the E to the minus power of the activation energy divided by RT. And since we're using this negative exponent, right, that is equivalent to saying A divided by E to the activation energy over RT, right? Those are equivalent expressions. Now, as we often do, whenever we've got something of interest in an exponent, we can get that out by taking a log. And so if we take the log of that expression, then you get the natural log of K, right? If you take the natural log, is equal to the natural log of A, right? Plus the natural log of this term that it's multiplied by, but since it's E, the natural log of that term is just the negative of the activation energy over RT. And if we rearrange that to put it in a linear equation form, right, then we can get that the natural log of the rate constant is equal to the negative of the activation energy over R times 1 over T minus the natural log of A. And so that puts us in a y equals mx plus b form, right, where the natural log of K becomes our y variable, minus activation energy over R becomes our slope, 1 over the temperature is our x variable, and the natural log of A minus the natural log of A becomes our y-intercept. And then, as we do, right, this is an equation very much in the same form as the Clausius-Clapeyron equation, and so we can do the same thing. We can subtract the two equations and adjust them, and we can show a two-point form of the equation, which is that the natural log of one K divided by the other, right? And remember, those are in parentheses, so it's the natural log of that ratio, right, is equal to the activation energy over R, 1 over T2, right? This temperature goes with this K, minus 1 over T1. This temperature goes with this K. Sometimes you see the form, right, if there's a negative sign here, then these two are reversed. Okay? Depends on who's deriving the equation and what the situation is. So those are our basic forms of the Arrhenius constant. Here we have some data where someone has done experiments at different temperatures for this reaction of, this is ethylene, dimerizing to form, that would be octene, right? So, I'm sorry, butene. Ethylene dimerizing to make butene, right? At different temperatures, and they've determined the Ks. Note, we can tell from the units of the rate constant that this is a second order process. Right? We should be able to tell that just by looking at the units of the rate constant. Right? But we've got, right, our Arrhenius equation in our linear form. And so when I plotted this, the first thing I had to do was to remember that I have to convert my temperatures to Kelvin, right? So 298, 318, or I'm sorry, 308, 318, 328, and 338, right? You have to convert those to Kelvin, and then we will make a plot that shows, right, on the x, or on the y-axis is the natural log of the rate constant. On the y-axis is 1 over the temperature. And when we do that, we get a plot that looks something like this. Right, where we get a nice straight line, and the slope of that straight line is negative 18,965. And looking at the units of that, right, rise has no units, run is 1 over T, so that is going to be in Kelvin units, right, because this is in 1 over Kelvin. Okay, so we've got 18,965 Kelvin, right, and that equals negative activation energy over R. So we've got negative 18,965 Kelvin equals negative activation energy over 8.314 joules per mole Kelvin, right? So we've got negative 18,695 Kelvin times 8.314 joules per mole Kelvin, right? Our Kelvin units cancel, and we get, okay? So looking, right? You always have to watch yourself, right? I made an error here transcribing, right? So that's 965. That's 965. I have to remember, because of this negative charge, or this negative sign, to put a negative sign here. So my negative times negative gives me a positive activation energy. We can't have a negative activation energy. And when we do that, we end up with 157,675 joules per mole. Rounding it to a reasonable number, right? We've got 2 significant figures in our Ks, so that would give us, right, to approximately 2 significant figures. 160 kilojoules per mole would be an appropriate answer. Okay, now we have another reaction. Here we have acetaldehyde in the gas phase decomposing to form methane, CH4, and carbon monoxide, CO, in the gas phase. And someone has done experiments, again, at different temperatures, right? So at 759 Kelvin, they found out that the rate constant is this. Again, it's second order, we can tell from the units of the rate constant. at 791 K, they found a different rate constant. The rate had gone up as the temperature went up. And so the question is, given those 2 points, what is the activation energy? Since it is a 2-point problem, we can use our 2-point form of the Arrhenius equation, which is that the natural log of K1 divided by K2 is equal to, right, the activation energy divided by R times 1 over T2 minus 1 over T1. And remember, those temperatures have to be in Kelvin. So if we start to work that out, right, we end up with, substituting those in, the natural log. I'm going to use them in order of 0.105, and I'm going to leave the units out. Since it's a ratio, the units are going of the rate constant are going to divide out anyway, right? We don't know the activation energy. That's our unknown. We know R in energy units, 8.314 joules per mole Kelvin. And we know temperature 2, 1 over 791 Kelvin, minus 1 over temperature 1, 1 over 759 Kelvin. Okay? If we do the math in parentheses and take the logs, then you end up with negative 1.18377 is equal to our activation energy over 8.314 joules per mole Kelvin, right? And this is 5.33 times 10 to the minus 5 per Kelvin units, right? Which, if we divide both sides by this, you end up with negative 1.18377, which is unitless, divided by 5.33 times 10 to the minus 5 per Kelvin. And then if we multiply both sides by this, times 8.314 joules per mole Kelvin, right? Our units cancel, and we end up getting 22,000 209.5 joules per mole, right? A reasonable number here, everything up above is 3 significant figures. I'm sorry, I misspoke. It's I misspoke. I was looking at the number that you get for calculating just this. If you do the math for the whole thing, since I'm running out of space here, you get 184,648 joules per mole, or to 3 significant figures, 184 kilojoules per mole, as a way to work it out. We're still working with that same reaction, acetaldehyde decomposing to form methane and carbon monoxide. right? We've determined the activation energy, and what I've written down there is the unrounded result. And so the next question is, now that we know the activation energy, what would be the value of our rate constant K at a third temperature, 840 K? This is another form of a two-point Arrhenius equation problem. And so we can use, right, this form, right? If we just adjust our left side, right, we can make that as, stop it. Right? It keeps trying to resize on me. That the natural log of K1 minus the natural log of K2 is equal to the activation energy over R 1 over T1 minus 1 over T two minus 1 over T1, right? We have to keep, right, if you realize you're getting, right, negative answers when you expect positive, you're probably switching your 2's and your 1's, right? So you have to pay attention to that as you're doing the problem. And so if we substitute into that, substitute our numbers, and since we want to solve for 1, I'm going to make 840, right? So this is going to be condition 1, just for convenience, okay? So the natural log of our K at 840 minus, and I'm going to pick 759 as 2, right? Minus the natural log of 0.105, and because it's natural logs, they come out unitless, so we don't have to worry about units. Right? Our activation energy is 184,648.45 joules per mole divided by 8.314 joules per mole Kelvin times 1 over 759 minus 1 over 840. And those are Kelvin. Right? And so we've got our equation. We just have to now solve for the natural log of K. Right? If you work out the math, which you should be able to do, right? You should be able to do that algebra. You get that the natural log of K at 840 is equal to 5.0754. That means K at 840 is equal to E raised to the 5.0754, right? That means, and if you do that out, you get K is 160, and then, right, all of that is unitless, so we have to go back to our initial problem to find units, right? All of our Ks are in the same units, so that's per molar per second. And that's how we would find K at a new temperature using the two-point Arrhenius equation. Our last question is a qualitative question. It has to do with catalysts, and it is, what effect does a catalyst have on each of the following conditions? But before we do that, we have to remember what it means to be a catalyst and what a catalyst does. And that's easiest to look at using a reaction energy diagram. So let's look at our reactant and our product. Let's make this an exothermic reaction, right? So this is delta H for the reaction in the forward direction, right? And so we have to go up let's change to this color, right? So if we look at this line and this line, right, that represents our activation energy, right? And we know from the Arrhenius equation that activation energy affects the rate constant, which affects the rate. So if a catalyst is going to make the reaction go faster, what it has to do is take the reaction by a path that has a lower activation energy, right? So this becomes our lower activation energy in the presence of our catalyst, okay? Right? And I shouldn't have done this, right? I think that's misleading because really it should continue down because we're continuing down to the same product level, right? So even in the presence of the catalyst, the delta H for the reaction is the same, right? That didn't change. The only thing that changed is we have a smaller activation energy barrier. Okay, so the question, what effect does a catalyst have on the activation energy? Well, clearly, right, that's lower, right? So it makes the activation energy lower, right? That's a straightforward situation, okay? B, what effect does it have on the forward rate? Well, if the activation energy barrier is lower, then more molecules at any moment have enough energy to get their arrangement, the arrangement of their atoms up to that transition state. And once they get to the transition state, they can fall to product. So clearly, the forward rate will be increased, right? The reaction will go faster. What about C? The reverse reaction rate. Well, if we consider the activation energy for the reverse reaction, the activation energy for the reverse reaction without catalyst would be that much. And with a catalyst, it would only be that much. So the reverse rate, right, the activation energy is also reduced for the reverse reaction, so the reverse rate would also be increased, right? And then if the last question is, what's the effect on the delta H for the reaction? Well, whether we are catalyzed or not, we're still dealing with this distance, right? So whether we're catalyzed or not, we're going from the energy of the reactant down to the energy of the product. Those are properties of the reactant and product. Those are not going to change. So the delta H for the reaction is unchanged because it is a property of the reactants and products themselves, not of how we get them from one place to the other. So I hope this helped you review your Arrhenius equation problems and your activation energy concepts in preparing for your exam. Thank you.